I'm Audrey Shulman. I'm the Executive Director of HEET, and I'd like to welcome you all to here. Thank you so much for being here. I'd like to acknowledge the presence of our utilities. We've got Eversource here, Columbia Gas, National Grid, and NiSource. I thank you for being here. I'd also like to appreciate I'd like to appreciate very much the our Senator. I got to go through this now. Senator Barrett's staff, Senator Warren's staff, Senator Cream's staff for being here today, as well as Representative Ehrlich's staff for being here, and City Councilor Jan Devereaux from Cambridge. I'd also like to thank all the state agencies, the engineers, academics, and the advocates for being here. Oh, and funders. Thank you for being here. So we're really looking forward to your feedback today. There are everybody should have gotten feedback cards. If you can, there'll be questions and answers at the end. But as you go along, if you have any thoughts or questions, please just jot them down on those cards. If you don't have one, ask us and we'll get them for you. This whole project has been a work of co-creation by many, many people in this group. And we'd like to ask you to all work with us to co-create more going forward to make this project possible. I'm trying to remember the next thing. We know it is not that you come here for us or even for BuroHappold Engineering, but you are here because you have hope, for collective hope, for a bright future going forward, in spite of all the challenges. I'd now like to introduce Zaina Magavi, HEET's research director, and a person without which not one bit of this project would have been possible.
All right, you also might be here for curiosity too. I would be. So one of those challenges, I'm just going to briefly introduce the challenge and then turn it over to BuroHappold Engineering. One of those challenges is providing reliable, affordable, and renewable energy to all, particularly in Massachusetts, heating. In Massachusetts, as many of you know, we have one of the oldest gas systems in the country, which you could look at as we were leaders in the late 1800s. But our state is currently reported to be about 26% leak prone statewide and over 40% leak prone in the city of Boston. Replacing that leaky pipe with new pipe, it makes it safer and it reduces leaks, and those things are good. But it is also a significant long-term investment. At utilities' current reported costs, the replacement will cost us, the ratepayers, over $9 billion. To give you an idea of what this effort looks like, it's very impressive. This is just the next 5 years of pipe replacement locations in the Boston area. And that's only a fraction of what will happen over the 20 years to come. So our Global Warming Solutions Act in Massachusetts mandates currently an 80% reduction in greenhouse gas by 2050 from 1990 levels. And many cities, Boston and Cambridge included, are already planning for a carbon-free future. So it is worth asking, are the gas pipes going in the ground today what we need in the energy future for tomorrow? So what we're sharing with you here today is another possible way to build a renewable and resilient energy future for our state. Street by street, we're proposing to replace our gas pipes with loops of pipe filled with water kept to a constant temperature by renewable geothermal energy, or the earth. We're calling these modular interconnectable loops GeoMicroDistricts. You can rename them if you want. So we asked BuroHappold, could geothermal boreholes in our streets, connected to a loop in the existing gas company right-of-way, provide enough energy to heat and cool all our buildings? If it could we then keep building and interconnecting these microdistricts until we have a renewable, resilient thermal energy system? Essentially, we asked them to build a model based on existing data for a system that doesn't yet exist. This is not easy. As with any model, what you get out depends on what you put in. So a sincere thanks to many people, to Eversource for sharing energy data to ensure our model is the best it can be, to MassCC for sharing existing ground source install data, to DOER, the Gray Edge Group, and so many others for ongoing and essential advice, and don't stop giving us advice. And so we have been privileged to work with an amazing team at the international energy engineering firm BuroHappold to take on these questions for the state of Massachusetts. If you don't know them, they did New York's 80 by 50 plan, an amazing heat map for London, and are generally on the forefront of rational, data-informed city and regional planning and engineering. So we asked them to use existing data and careful, reasonable, and transparent assumptions. Where unsure of accuracy, use multiple choices to provide a range of outcomes, and basically answer the question, is this idea worth moving forward? So I'm turning it over to Alex Stelk to share his answer.
Thank you. Hi, good morning, everyone. Yeah, so about 4 months ago, let me know if you can't hear me because this is a little wonky. About 4 months ago, we put in a bid for this feasibility study with HEET to try and answer the questions that Zainab just posed. Really, what's the feasibility of replacing existing natural gas infrastructure with a, basically a geothermal heat pump system? And as she said, this was for the state, for all different building types. And so if you're someone who's in the ground source heat pump space, you're probably saying, wait, what? Like, what are the ground conditions? What are the building types? That's a lot of different stuff. And that was true, and it made it incredibly difficult. And so to address that, we kind of approached this at a very high level, looking across the state at a number of different building types to try and provide a reasonable answer to that question. So the scope of the project was broken up into about 5 tasks. The middle 3 were the meat of it. So we had a preliminary analysis when we were looking at Massachusetts as a whole. What are the different types of geology, soil conditions? We were looking at the building types. What was their typical energy consumption? What was the typical density layout of the blocks? And we used that to inform our assumptions. So on one side we had, there used to be more stuff there. On one side we had the site conditions, everything that I just spoke about. And on the other side we had the system size and the cost, which would be informed by the building side stuff, our cost estimates. And they came together to inform what would actually result, if this could actually work. We considered 3 types of geothermal or ground source heat pump technologies. First, ground coupled systems, which basically use the earth, soil, bedrock, as a heat source and sink. We considered groundwater systems, which you use water in the ground, such as aquifers, and then surface water systems. Ultimately, we just did the ground coupled systems because they are, by and large, the most commonly installed systems throughout this state and kind of everywhere in general. You also avoid issues with environmental issues, water contamination, things like that. And the permitting process is ostensibly easier with these types of systems. So key considerations. First were the thermal sources. So, across the state, if you choose some site, what is the capacity going to be for a ground source system? We looked at land use for a given site, say a street. How many buildings are on that street? What are the size? How closely are they spaced? And then we also looked at building energy consumption. So for all those buildings on the street, how much heating and cooling loads need to actually be met by the system. So in terms of the the thermal sources, there's a fairly wide range of different types of rock across the state. It's mostly granite and metamorphic. That probably doesn't mean anything to you, but it has pretty good thermal conductivity. It's usually located about 5 to 40 feet below the surface. So as we started to calculate things, we used an average depth from this. And then in terms of developed land across the state, a fair amount of it is residential. It's mostly kind of medium to low density residential with a few other commercial and few industrial uses mixed in. So this kind of formed the basis of our assumptions for how we're going to approach this problem, because remember, we're trying to answer a question about a specific system for the entire state. So for the different building types, we developed 5 different building energy profiles, which were based on data for these building types from national data sets, also some state data sets. And then we created these annual energy consumption profiles. We also considered energy efficiency, because you're not going to want to install one of these systems if you don't do some sort of energy efficiency retrofit in an existing building, because you'd just be wasting money, right? You want to improve your energy efficiency before you install these things so that you're installing a smaller and thus less costly system. And then we looked at the end use, and this is what gave us our cooling and our heating loads. This is what we had to meet with the geothermal system to make it viable. So the approach, based on the aforementioned kind of understanding of land use, we developed 4 prototypical street segments that were based off typical building sizes, typical lot sizes, and typical right-of-way sizes across the state, and then kind of more specifically in the greater Boston area, because we could have more concrete data for that. And so for each of those prototype street segments, we applied those building energy profiles to each one of those buildings, and then combined it in a way so that we could account for the coincident demand, right? So if one building is using heating and one building is using cooling, they can kind of cancel out. If they're occurring on different times of the day, then you don't have to size it to the sum of all the peak loads. You can lower it a little bit. So we accounted for that. We assumed that it would be either a closed horizontal or vertical ground coupled heat pump system. We assumed that the buildings would have their own heat pumps and they'd be connected to a thermal loop that was outside and potentially owned by a utility. And this is a key point, we also assumed that it would maintain a seasonal energy balance of about 10%. That means that the amount of heat that you're putting into the ground and the amount of heat that you're pulling out of the ground during the heating and the cooling season is more or less the same. And we did this to avoid thermal degradation, right? So if there's an imbalance between the heating and the cooling, or the heat being put in and the heat being taken out, it could lead to adverse conditions, right? So you're either freezing the ground or you're heating up the ground too much. So this would diminish the capacity of the system and make it work less well, and then also lead to environmental issues potentially. And so we wanted to avoid that. A key thing for that is, if it's a standalone system, there's not much you can do. You can find other sources of heat to kind of put into the ground to balance that out, or to take it out. But with this kind of GeoMicroDistrict model, because the systems are interconnected, you have more opportunities to increase diversity. So some buildings may be using heating, some buildings may be using cooling more than others, and that kind of evens everything out, and it allows the system to operate much more efficiently. And then we also looked at cost, which I think is what everyone is probably most interested in beyond the actual technical feasibility. So in terms of installation cost, and again, there was a huge range for what we could find and what was considered. We tried to account for the equipment and labor of actually installing the systems. We tried to provide allowances for design and engineering, the permits and approvals that would come with digging up the street and putting in these types of systems, overhead, profit, contingency, and then also a little bit just to account for the economies of scale. Because sometimes we have price data for like a single heat pump, which is fine, but if you're installing multiple ones, or not a heat pump, a water pump, whatever, you're gonna have some sort of discount. In terms of the rates, so if this were a utility-owned system, they would be charging customers per therm or per MMBTU. We did something that I call like a pseudo rate case, where we assumed a 60-year amortization period, which is basically the life of the pipes themselves, 7.5% return on equity, which is what the utility can take a profit off of, and that's just for the capital investment. And then we passed on the operational cost of like running the circulation pumps to the customer. And that gave us like a rate. So we could kind of compare, you know, if you were a homeowner or a commercial building paying for natural gas now, if this were installed on your street, what would you be paying for that in the future? And again, so this is tough. This is from Mass CEC. This is their small scale residential program, a residential ground source heat pump program. This is the range. There's not a strong correlation between the size of the system and the cost. Now, granted, some of these may be inflated. These are reported and they're to get rebates, to get incentives. So there's some variability here, but this is just to make the point that there's not a lot of good information out there currently about what it would cost to actually install these systems in an individual home, let alone on a street segment in this configuration. And then for the customer cost, again, we assume that they would be doing kind of minor energy efficiency retrofits. So that's insulation, like a white or cool roof in some instances, and then air sealing. And this would just help reduce your heating and cooling loads. We assume there'd be a conversion from their existing heating and cooling system to a heat pump that would connect to this GeoMicroDistrict system. And we also assume that, you know, if you were a residential customer and you had a gas stove, you would need to replace that with an electric stove. If you had a gas dryer, in some cases, you would have to replace that with an electric dryer. So we accounted for that as well. But we also did consider the existing kind of incentive programs through Mass CEC and Mass Save and applied those. And this is kind of like the overall picture of what we considered. And I'm sorry if it's dense. At the end of the day, the closed horizontal systems really didn't perform that well. And partially that was because you don't have so much room in the street in the right of way to begin with. So it was difficult to size those to an extent where you could actually meet 100% of heating and cooling loads. This is not to say that it's impossible. We purposefully did not consider installations that would go in, say, a parking lot, a park, a private yard. We just focused on the right of way, and to the extent possible, we tried to focus on that 2-inch strip of natural gas utility right of way. You could say that this is, if not the worst case, a very conservative 2 foot.
You said 2-inch.
Oh, no, it's 2 feet. It's definitely 2 feet. The closed vertical actually performed quite well. So this is a best case scenario. And if you remember the thermal imbalance I was talking about, this doesn't necessarily account for that, not yet. But if we just open it all up, we can meet 100% of heating and cooling loads in 2 out of the 3 kind of prototypes that we studied. And for the medium density residential, you can meet 100% of your cooling loads, but not your heating loads. High density mixed use, pretty difficult, but these are also land uses that would be in a place like Boston where you would already face a lot of problems in terms of existing infrastructure in the street. So that wasn't a huge loss. So what does it look like? This is a very generic model of what a vertical system might look like in a utility right away. So we have this horizontal thermal loop with service going to each of the homes or the buildings. And then we have a line of boreholes that are 20 feet on center. And each of those boreholes has a U-shaped tube that goes down and back. And it circulates heating and cooling to each of these buildings. It can coexist with other pieces of infrastructure. Even if you have a separated sewer, it can still fit somewhat easily between these things. So in terms of getting everything into the street, we think it's probably fairly feasible to do. And if as we get into this, you'll see that we have more than this. So we have actually 2 lines, which, as you can see, there's still a little bit of space left over. It wouldn't be this orderly in the real world. I can see Kathy Watkins laughing. But I hope this kind of like clarifies what this would actually look like. So for the medium density mixed use, this was kind of like our best candidate because you had, you know, a fair diversity of loads because you had some retail commercial uses. So you had the cooling that could kind of balance out the heating. Under the balance condition, where we're saying we don't want to even address thermal degradation, we want to be safe. You can meet 100% of your heating loads in this situation and about 60% of your cooling loads. If you were to open it up and interconnect, you can meet 100% of both loads, and you would need to export that heating energy somewhere else so that you can maintain that thermal balance, at least for those boreholes. In terms of the actual energy prices, when we did our faux rate case, the ground source heat pump actually turned out to be lower than the natural gas, at least for residential, and pretty much on par for commercial. And both, as you know, are significantly lower than the cost of electricity. But of course, there are different efficiencies and they're used in different ways. When you look at the actual annual energy cost per building, you still have some savings. So the 2 purple bars represent what the annual cost per building would be for a customer in this configuration. The gray bar going south below the dark line, that's the amount of energy, or that's the amount of money that you would be saving per year with this install. And this is just in terms of energy costs. It's not yet accounting for, you know, what it would take to actually convert or install this system. And so on that note, in that configuration, a lot of the costs for installation are associated with the borehole drilling, which is fairly typical. Sorry, I can't read this too well. Yeah, this is the main cost because, yeah. Be fine. No, there is a point I want to make, but it's not on this one. For residential conversion, a lot of the cost, of course, goes to the heat pump installation itself. Because in this case, we're looking at the balance, you would need to add in that's the next one, sorry, early morning. You would also pay some for the new appliances as well. On the commercial side, this is where the cooling really kicks in, or the lack thereof. So because you aren't able to meet 100% of your heating and cooling loads for the commercial buildings where you had relatively higher cooling loads, you would need to retrofit with some sort of a air source heat pump cooling system that could be integrated with the ground source system to provide kind of that heating and cooling load. And this, even though you're paying more upfront to install a new cooling system, it actually nets out over time because the amount of money that you save just converting to an air source heat pump and getting around the cost you would pay for electricity in a typical air conditioning system makes it less expensive in the long run. So in terms of the actual, return on investment, initial investment, this is an average. We had about $500,000 for the ground source heat pump installation, and that would be taken on by the utility. And with the kind of the assumptions that we had, it would result in about a 44-year payback period. And this is over a 60-year, time horizon. For the residential conversion, after rebates and other incentives, it would be about $5,000 per unit. So that's per condo unit with a 24-year payback. And a lot of that payback would be coming from savings in your electricity cost. And for the commercial conversion, it'd be about $80,000 per building, which works out to about a 37-year payback. So on the other end of the spectrum, for low density residential, when it's in a balanced condition, you can meet 100% of your cooling loads, but only about 30% of your heating loads. Whereas if you open it up again, you would meet both loads, but you have a significant amount of cooling energy to export in this case. And this could be taken off by something like an ice hockey rink, commercial, cold storage, anything that would need cooling. So you could interconnect that type of use to that and make the system more feasible. But for the balance condition, because you're not meeting 100% of your heating loads, you would also need some sort of backup heating. So that's where you would have a natural gas generator, potentially providing heating off-site and managed by the utility. And that would start to represent a little bit higher cost. But on the residential side, still the story is the same. A lot of it is the heat pump installation, a little bit more in terms of new appliances. And in this case, the initial investment is lower at $340,000 with a 22-year payback. And the residential conversion cost is a little bit higher at $7,500 per building with about a 20-year payback. So overall, and this is the summary, this seasonal imbalance is the main kind of issue in terms of capacity. It's not the fact that you can't install enough boreholes, it's that you need to be able to mitigate this issue, or else you face those ground condition issues. Like I said before, the closed vertical systems were the most feasible for all systems that we analyzed. And the closed horizontal systems, they could be used in certain conditions, but don't have the kind of like broad feasibility that the vertical systems have. In terms of the economic observations, there's a wide range of cost for installation and conversion. We took pretty middle of the road and conservative estimates that don't necessarily account for the different types of existing heating and cooling and distribution systems. They don't account for the conditions you may have on the street, the density of infrastructure, the cost of permitting. So, you know, at the end of the day, there needs to be more information. But that being said, from what we've seen and from our conservative standpoint, it does seem economically feasible. And yeah, the costs are highly sensitive. Finally, we just studied a single street segment. And so we didn't really pick up on the types of benefits and efficiencies that you would get from interconnected systems. So if you have more customers, you increase the rate base and you're able to spread those costs around even more, which would result in lower annual energy cost for everyone that was connected. And then you also get those diversity benefits in terms of running the system at a higher efficiency. So yeah, that's it. I'm sorry I hit you with a lot of information, but yeah, happy to answer any questions.
So we'll take questions and answers at the end. Everybody can hear me okay? I'm worried about this mic. So I'm gonna, because I'm probably the only liberal arts major up here, I'm gonna just explain what this might mean in your own home for those people who are not scientists. How does, you know, we're all basically Neanderthals, right? And we expect if we want heat, we gotta burn something, wood, gas, something. So how is it that this new technology, these heat pumps actually work? Well, they aren't all that new. We've had this technology, all of us have grown up with it. It's in your fridge. And the technology works, right? On a really hot day when it's 95 degrees in my house, I can go to my freezer, open it up, and find the popsicles are still frozen. What a heat pump does is the same as your fridge. It moves temperature instead of creating it. So for every, you know, so in the summer, it moves heat out of your house. In the winter, it moves heat into your home. Because it's moving heat and not creating it, it's much more efficient. For every 1 unit of electricity energy used, it can move 4 or more units of temperature, of heating or cooling. In your own home, what would happen in my home? It would, instead of having gas in a service line being piped into my basement, I would have water in a pipe being brought to my basement at a constant temperature. In my basement would be a heat exchanger or a heat pump, and that would pump the heat off that it wanted, you know, that I needed, off of that from the water and use, put that through my distribution system, which in my case turns out to be a radiator. And my neighbor, I could have my house at 65 degrees, my neighbor could have it at 75 degrees, she could have a different kind of distribution system, it would all work out. The water would be returned afterward at a different temperature. If I took a lot of heat off, the water would be returned cooler, right? The boreholes underneath the street would return the water to the original temperature so the other homes could take from that to get their own temperature. You don't see a lot of geothermal systems installed in Massachusetts, and that's mostly because here, it's generally just one building at a time. That doesn't allow for, that's really gonna jack up the cost, right? 60% of the cost with geothermal is simply getting the drill rig to the site. If you do 100 buildings instead at a time, street after street, that's gonna really drop the price. The next problem, however, is if all of the buildings are exactly the same with the same, all homes with the same sort of energy use, they're all gonna be wanting heat, in the winter between like 5 and 7 a.m. That's not gonna allow for a lot of efficiencies. So it's with mixed use instead that you see the greatest possible gains, as Alex said. If you have that, then you have an office building or a supermarket or a hockey rink or a data center, taking an enormous amount of cooling off the system and returning the water hot that then can be reused in the homes down the street or can be stored in the ground. Because the ground can store that energy, that temperature for a really long time. The more diverse the use, the more efficient the system, because it can then take the wasted energy and either reuse it or store it. And because it turns out that the biggest energy storage system on the planet is the planet.
So I hope I'm not going to try, how are we all doing? I hope I'm not going to try your patience by telling you a few more things. We just want you to know a few more things, and then we're going to do questions and answers. So in case you're wondering, we aren't the only ones that are onto this idea. The International Ground Source Heat Pump Association is currently writing their first set of code for shared loop geothermal. In part because of the excitement of a number of case studies like this one here, Colorado Mesa University. It's in Grand Junction, Colorado, so yes, they have snow too. And it was built by Gray Edge Group's Carrie Smith. And let's see, I've got some numbers. It is a 4,000 ton system. It serves 16 buildings totaling 1.2 million square feet. The gas backup hasn't fired in more than 10 years. And the performance has continuously improved as they've added buildings to the system, just as expected. So we're working with them to get this case study out, and we're collecting a lot more case studies. And we're connecting to all kinds of experts like Gray Edge and some of the folks here today. But we're also collecting potential system benefits. And to me, this is really exciting. So humor me. Let's see, I need a clicker. All right, I'm gonna run through these quickly. So Audrey's right. The largest long-term energy storage on Earth is the Earth. And it may also be the cheapest. As we move to more sun and wind energy, long-term storage is increasingly important for our electric grid, and our proposed network could serve as storage, and it can also connect to additional storage reservoirs. The system also helps the electric grid go renewable by cutting summer peaks. Geothermal is known to do this, but brought to scale as suggested, the impact could be very significant as our summers get hotter. And those hotter summers, one prediction, I believe for Cambridge, suggests that we will transition from a heating climate, like dominant heating, to a cooling climate, dominant cooling, in 2070. So that's extraordinary. And none of our current systems are designed for that. The system we're proposing is inherently flexible and can adapt to our changing needs, which I think is important. It can also be integrated, as Alex shared, into infrastructure plans under our streets, like the City of Boston's proposed utility corridors. And, you know, I think it'd be great if we put our electric wires underground at the same time while we're digging up the streets. Things that are underground are inherently resilient, particularly in disasters. The GeoMicroDistrict, with its fusion of local energy generation and interconnected energy management, is inherently a resilient design. And it's safe. If a pipe, for example, gets overpressurized, we could cope with the resulting puddle. Finally, and I think most importantly, Massachusetts is currently pursuing renewable heat one house at a time, meaning it's mostly those with means and motivation that are transitioning, and it's not fast enough. Creating a renewable thermal utility can ensure that all of our residents have equal and affordable access to clean, safe, renewable heat and cooling. All right, so my list can go on, but I'm going to stop, I promise. And let's talk about moving this idea forward. We need clearly to move from a desktop feasibility study to a pilot in the ground so that we can get real data to work with and plan with here in Massachusetts. To do that, we of course need all of you, your feedback, get your cards, your ideas, your support, and we need pilot site locations. As of today, we're building a database of the willing, people who, given a choice, are willing to consider joining a pilot. Did I mention free weatherization and appliances? Please let us know if you're one of them. We have also already begun meeting with towns, with housing authorities, municipal utilities, anyone who will talk to us, to collect many possible sites. With multiple potential sites in hand, then comes the design and install, request for proposals, and eventually the breaking ground. Obviously, there are 100 or more steps within each of those next steps and a lot of work, especially to do this as fast as we would like to. But we believe the time is now. As we invest heavily in gas infrastructure, we need to look at whether this is the right choice for Massachusetts. So it is essential at this stage that we spread the idea. And one way HEET is doing that, together with Mothers Out Front, has been hosting Taste the Future cooking events. These events, of course, have good food, but they also educate people about induction cooking, heat pumps, and other renewable-ready appliances. After all, we need the will of the people behind this effort if it's going to happen. And hopefully, with the will of the people, the Future Act legislation can serve to clear the way for our gas utilities to choose to transition to renewable thermal and be rewarded for that choice. Again, spreading the word, supporting these efforts at any level will help make it happen better and faster. And we really, really do want to share. To be clear, all of our slides, our work, our ideas, and the results of this feasibility are made available to you for open sharing and adapting under a Creative Commons license. At HEET, we believe that given the urgency of climate change, we need to spread good ideas and iterate as quickly as possible. So we're really serious when we say we want to co-create this climate solution with you. Finally, we're done. Thank you. Again, one second. Okay, almost done, I promise. For helping us get the idea this far, and for having, as Audrey said at the very beginning, hope. And perhaps in 2030, when my oldest daughter is 27, she'll get her first apartment and pay her first utility bills. So exciting, right? And have two utilities competing to deliver her renewable energy safely, reliably, and cheaply. She'll have wires bringing her renewable electricity and pipes underground bringing her renewable thermal energy, both of which she will likely totally ignore. But she'll have a choice, and she'll also have a livable climate. Thank you.
This is Bill Herkins on HEET's board, and
They brought me up just so we could change the face up here. So this is the question and answer period. So what I'll try to do is get as many questions as we can. How much time do you think we have, Audrey?
15, 20 minutes.
Okay, so, all right, the lady down and back right there.
The first one is that Audrey showed a slide that said single building geothermal is expensive. I'm a residential architect, and I just wanted to say that in our experience with the 30% federal tax credits and the Massachusetts tax rebates, that that adds up to almost equalizing costs. I mean, it did 10 years ago, and I think we're in the process of pricing out a project right now. So actually, I would just say that single building geothermal is not necessarily expensive, and also the operational costs are a fraction of what they are for fossil fuels. And then the second question is just to ask about how you calculated your quote-unquote payback, because I know, and one question to add into that is that I know that New York is now, I think at least New York City is now going to require in the near future that people pay for their carbon emissions that the buildings do, the new buildings do. So was any sort of carbon emission payback involved in that?
So
Also, how did you actually calculate the payback?
okay, so
Come here.
yeah, can I take this out? Okay, cool, much better. Yeah, so you're right. In New York State, 2 weeks ago, last week, just passed new legislation that would basically mandate all buildings, new and existing, to hit a GHG target of 23 and then 2030, I believe. We did not account for those cost savings or those avoided costs. Again, we tried to, really make the most conservative estimates that we could, because we would rather people say, hey, that costs too much. It would actually be cheaper than you underestimated how much investment this would take. So there's that. For the payback, we essentially took to get into the weeds, we took the installation costs, we applied the Mass CEC rebates, and did, I think, the Mass Save financing, 0% financing over 7 years, I believe it is. So we accounted for all that in the payments. We took the avoided costs of energy, so the avoided cost of natural gas and electricity for heating and cooling as profit. Over that 60-year period, we applied a discount rate of, let's say, 5%, whatever the standard rate is right now from the Fed, and then just basically looked at where the cost curve went above zero. So it was probably more robust than it needed to be based on the quality of information that we had going in, but we tried to account for all those factors, and we tried to be as conservative as possible.
And I just want to apologize. I meant expensive relative to doing a lot of install. Right?
Sorry.
Always be,
No, but I just wanted to because I didn't want people to go.
Please use the microphone if you can.
expensive relative to many installations.
All right, Matthew?
Groundwater, heat transfer, and I look at how you couple the heat from the pipe to the ground. If you get a hole that's different than the pipe, it needs to be in full contact with the rock in some way.
Yeah, it's in a tube-filled grout that has a conductive heat to it.
You refill after the
Yeah.
fact.
If they're installers in the room that actually want to.
Lamentably, we're all dependent upon a thing called flow. And with a single pump, you won't get terminal flow, and you won't get the heat exchange. So that's a small item in the program. So having a single pump on these multiple loops, unless everybody's running all at once, you're not going to get the heat exchange. You have to have what the engineers call turbulent flow. The water's rolling against the side of the pipe. That's a small change. There are systems in Massachusetts that went in 1981 in Worcester area. They're community that are working fine with well water.
Remote participants are unable to hear.
30% less expensive. And I think that would have had a major impact on the cost analysis.
Actually, do you want to?
So we have, hi, I'm Rocha Yada. I'm also a consultant at BuroHappold Engineering and worked on a lot of engineering aspects of this project. So to answer your question, we did take groundwater systems into account.
Could you summarize the question for us?
For looking at technologies that could be installed in the public right of way, installing it as like in the public right of way did not seem like a great idea for many reasons. But you're absolutely right. The conductivity of it, like when you're using groundwater heat pumps is much better as opposed to groundwater heat pumps. It was just a matter of finding the most feasible technology that could be installed anywhere in Massachusetts. And in addition to that, when you are trying to install groundwater heat pumps, there are a lot of permitting issues and a lot of like distances that you have to maintain from like other infrastructure systems, like be it like your sanitary sewers, be it your potable water. So you have to maintain the distance of anywhere between 10 to 25 feet. And when you have a public right of way corridor, which is only 40 feet, there is not that much room to install groundwater heat pumps. That said, you could always install groundwater heat pumps at like a central location and interconnected with a system that we propose. I hope that answers the question.
I have another question,
Yes.
separate from that. Okay. Hi. I'm wondering, with the benefit of having the utility companies in the room, which I'm delighted by, whether they could give us a sense of whether this has been on their research and development map, this concept, and what they might be doing independent, of this pilot one going ahead. Just trying to get a little sense of where it is on the radar screen of utilities at this point.
Any of the, Dan, Bill, and Dan and then Bill?
Just a comment, conceptually, there has not been a lot of analysis by the gas utilities to date. This proposal, quite honestly, would be the impetus for that kind of analysis. Because of the historic utility rate-making construct, it did not favor our investment in speculative technology. There was absolutely no incentive. And in fact, there were a number of disincentives if you invested in a new technology and it didn't prove to be as effective as you hoped. You could have those costs disallowed. So it was essentially a way for utilities to lose money and absolutely no incentive to invest. Those paradigms are now changing, but without that, it was historically incorrect.
Can you identify who you're with?
Oh, I'm sorry. I am with Mike.
Okay.
NiSource is the parent company of Columbia Gas and one of the largest utilities in the country. Bill, from Eversource Gas.
Before we go sneaking, stay in the back of the room. A couple things. One, we're hugely invested in the 4,000 megawatts potential offshore wind in this region being developed and partnered with some of the biggest companies on the planet Earth that bring that to us. Obviously, 70 megawatts of solar now up and running utility scale in Massachusetts. Some 5,000 EV charging stations being deployed over the next three years. So all that, to answer the question, has led us to a lot of places where we're looking, especially in the natural gas side, to the clean energy. So power to energy, renewable natural gas, and obviously, the very moment that they have and Audrey brought this concept to us, we've been deeply involved. There's a lot of heat pump new technology around for a while. So we've been looking at what works, what doesn't work. This is a very intriguing model. It brings some challenge, some unique benefits from being utility scale versus the standalone. The balancing of heat and all this stuff. A lot of this model is very, it's going to be a very engaged and hopefully aspire to hopefully be a pilot, literally a pilot organization. So I think that's where we really go. But we're all in.
All right.
National Grid actually does have a pilot project for geothermal in our New York jurisdiction that we've been right now. But we have 10 homes connected to a shared loop in Long Island. That's been up and running for over a season now. We want a house right now. And we've also proposed doing additional expanded pilot as business models like this. So I think National Grid is very excited. I know.
Gentleman right here.
Okay,
Introduce you.
Steve Fink. I live in a community that's seriously considering a change in how we do all this. And there's some redevelopment going on that offers an opportunity. I may ask this question poorly, so somebody re-ask the question if I don't do it as well. We're considering microgrids and this technology. And I have friends who have installed.
Can you stand up and speak loudly? 'Cause I think
Sure.
there's something
And
going
identify
on.
yourself, again. I'm Steve Fink. I'm from a North Shore community that's currently considering microgrids and this sort of technology for a redevelopment we're doing on town. I don't really know what I'm talking about, but I'm learning a lot quickly. And I'm not sure I can ask this question correctly. So anyone, and we have a great relationship with Columbia Gas, so I think you'll hint at one of the 3 towns that I'm from. Absolutely superb relationship. The question is, over here we've got this technology. Over there we've got microgrids, and we're talking about renewable electric, okay, or clean electric energy. I'm trying to figure out how our town can evaluate these 2 technologies and figure out what the balance is. The question makes sense?
Sure.
Yeah, they're not usually exclusive at all.
How do we figure it out?
How do you figure out which one to do? So, I mean, the microgrid is a slightly different application. So, a microgrid is where you have a, you can call it a neighborhood that's islandable, right? So, it can be detached from the grid. It can run on its own. You're going to have some sources of generation. It could be a combined heat and power, natural gas thing, whatever, but it's providing you with electricity. The benefit of it is you can disconnect from the grid when the grid goes down. You can put whatever generation source you want on, and you can be self-contained. This system, it's just a totally different system. It's just like a giant air conditioner / heater that you stick in the ground, which can be run off the microgrid. And in fact, it would be even better run off the microgrid because you have even more resiliency. Because that means that if the power system goes down, the gas system goes down, you basically have a self-sustained community. And then you could probably further reduce your energy costs because you're not paying. There's still a little bit of electricity that you need, probably more than a little bit, to actually run the pumps. So you would kind of be closing that loop where you would be handling everything yourself. Does that make sense?
Still looking for that
What's
spreadsheet you're going to have.
Oh, the spreadsheet.
Good luck.
I want to say we will, with BuroHappold's permission, be sharing the spreadsheet with the utilities so that they can begin to put pressure on all these numbers and make sure it works. And for me, I would love to have, I think both systems would be great because then you, in the same place, because then you have electricity islands and heating and cooling islands in the event of climate change disasters.
We might be able to do both at the same time. This is such a disruptive project.
Paul.
Hi, my name is Paul from the Department of Energy Resources. I have a question. Oh, this isn't filled out.
Yeah.
My question is, the payback that you presented, does or does that not include a credit for the avoided gas replacement cost? And if it does not, what would the payback be?
Yes, it includes the cost of avoided gas replacement.
Okay.
But because of the way that it's structured, you know, the utility payback is always going to be longer by design. It's meant to be that. They collect profit off of the install and then they pass on the other costs and it's spread out over 60 years. I mean, that's the model. The cost of, you know, at the end of the day, yeah, it's going to cost more to dig a ton of holes in the ground and install a new geothermal system than it is to just tear out old pipe. But we did come to that.
Maybe right here, please.
Hi, my name is Amy Tai. I work in the Mesa Fund, and I understand that calculating costs is a really, really important part of our world today. I wonder if the cost of the subsidies that we give to fossil fuels in general was calculated into the general cost. And obviously, costs for climate change, climate crisis cannot be calculated if we're thinking about like long-term costs, health benefits, disaster relief, et cetera, but how can we calculate those costs into a study like this? And can we? And is it a question that we should be all asking? Like, is it even really necessary to think about the dollar line for Massachusetts? So.
That's a really good question. I'm sorry, I'm Adam Freeberg. I lead the city's team for BuroHappold. That's a really good question. It's, you know, and I think over the last, you can say 10 years, some of those subsidies, and there's still subsidies, the fossil fuel industry are moving a little bit more towards investing in renewables. But yes, benefits. We want to cost those things. We want to try to do our best, whether it's the cost of carbon, for example, in New York State, if you're doing some type of, any type of really infrastructure feasibility study, you're including the cost of carbon in that, even though, you know, it's not fully there yet. The cost of health impacts, you know, there's more and more, we know more and more about it than we ever did. You know, in California, I would say we're doing a project right now in Los Angeles where we're including the benefits of reducing fossil fuels and traffic off the road by looking at the health impacts and the asset impacts. And those are all costs. Those are all costs that hit us. So yes, we'd like to include, you know, these type of costs, whether it's for safety, the impacts of some type of accident, the impacts of more traffic because of some type of disaster as a result of climate change or other means. But yes, I mean, that's where we're starting to get more of that information. And to me, there's no reason why we couldn't include some type of externality cost, and also more importantly, the benefits, whether qualitatively, once again, we'd like to get more quantitative as we get more of that data into these things, because they are costs, they are societal costs that we're, you know, starting to get better information on.
Yeah, and I also wanted to make a point about, like, for the utility, not that, like, you don't really care what the is for the utility. I don't care. The main point, sorry guys, the main point was that we wanted to make sure that, you know, with the utility business model, what the actual rate would be for that energy wouldn't be too much on the number, and the actual installation cost would be building there. Because whatever happens, like, we don't want this to, you know, be prohibitively expensive for anyone that lives in a building. So that was kind of like the driver behind that, just understanding that, you know, it wouldn't be some high in the sky.
I just want to add that with the customer cost, that number is not considering the fact that some of the appliances might already be old and need to be replaced, right? So, you know, in my house, I need to replace my, you know, the dryer and, you know, the heating system. Then that would really, I'm gonna have to pay that money anyway. So.
Oh, the gentleman in the back.
That's where you come in.
Repeat the question.
So the question was, how do you get a neighborhood to agree all at the same time? So what we're going to do is we're going to do Taste the Future parties. They're induction cooking parties where we show off, because most people don't care how their heating is delivered, what fuel is used, or how their cooling is, you know, so long as it's not expensive and, you know, it's warm or cool, it's the temperature they want, right? So the main thing people care about is their, you know, in terms of fuel, is their gas stoves, because they think it's the best kind of cooking. So we're going to do parties where we showcase induction cooking, showing that it's safer, faster, more precise, and healthier, so that people can get used to cooking using induction. We'll also create maps, and we probably haven't told the utilities this, so showing where the the public, you know, where the leak prone infrastructure is, so that we can target those areas. And the places where the pipes have to be replaced. And then we're relying on you to talk about it, to connect with others, to make it, to have people understand why we need to move this way if we want our children to be able to have a livable future. Right?
Nathan?
I just wanted to add that Audrey's comment that
Yeah, I just want to acknowledge that that is kind of the million dollar next big question, is how to get a whole street segment that is a reasonable location that does need pipe replaced to a grid. And we have a number of different ideas, and we're open to other ideas. And Project Out Front has agreed to help with outreach. But also, if there's, say, you know, a whole bunch of people that come together, but one person says, "Oh no, I'm not doing it," there's those propane tanks. Just saying.
All right, this gentleman here is very important.
My name is Peter Lavish. I'm a member of the Green Committee of our neighborhoods, which is the back day. And I wonder whether the individual systems, whether front, so heat pump or microgrids, are scalable if one adopts one or both systems. And then how do you link up with it with your neighbors and others?
So that is actually a very good question. So the whole idea here was to like have shared loops that are like connecting to like multiple buildings in one street, and then eventually interconnect them with like similar shared loops in other streets. So yes, this is a scalable model. To answer your question about microgrids specifically, it's like every time you go to interconnect an additional system, you have to sort of do the exercise of estimating capacities with the energy demands for the connected system iterated again and again. Yes. So, like for example, we gave you the example of like a low residential neighborhood and a mixed-use neighborhood where one had higher heating, whereas the other had higher cooling. So it would be a wonderful idea to actually connect those two systems together, because then you would require lesser backup for heating and for cooling. So the ingenuity of the solution lies in how best we can connect these different systems and how we can like target the right street segments to connect with each other. And the system becomes more and more resilient as you sort of connect them all together. I hope that answers your question.
Just a couple of comments, if I may.
What the fuck?
Number one,
Stop.
Having spent a career digging in public right-of-ways, is coupling your projects with municipal improvement. Because the restoration costs can run from 20% of a project cost to 100% of a project cost based on the way the city chooses to require ultimate street restoration. So that is absolutely essential in my view in managing costs. The second thing is, and both of these, frankly, organizations like HEET can really influence public policy. Public policy will make or break this, because the reality is in today's utility construct, we cannot deny service. If we are serving a customer today, we cannot unilaterally elect to terminate that service for any reason. So it really would take unanimity in these projects. And so sort of coupling that, I think, Audrey, you called it a coalition of the willing. That coalition also has to include those stakeholders, the municipalities, every person on the street, other key stakeholders if this is ultimately going to become reality. So just without wanting to sound negative, those are the realities, particularly in terms of cost. The third thing, just one other one from a technical standpoint, guys. Again, having spent a lifetime in the right-of-way, particularly narrow right-of-ways in New England, 2 feet in my mind is not enough right-of-way to do what you propose. With vertical boreholes and horizontal pipe, maybe 8, 10, or 12 inch in diameter, 2 pipes. You simply can't do it in that. That has to be spread out so that longer term maintenance can be realized. You need to be able to excavate down 5 or 6 feet to the backhoe. In order to do that, you simply need more room than you're envisioning. So again, as a side, I think, you know, we who have spent a lifetime working on that stuff can probably help you with some of those designs, but just 3 comments for you to consider.
Yeah, actually cannot emphasize on that point enough. Like if you're going to replace your sidewalks, consider installing geothermal pipes. If you're going to replace your water pipes or sanitary sewers, consider installing geothermal pipes. Although the premise of this project is all about replacing natural gas pipes, he's absolutely right. Like the reconstruction costs that are associated with like repaving roads can like make or break this project. So
Okay, maybe one more question.
Hi, John Schmacko, I'm an Aztec from New York, actually. And we have a lot going on there in terms of thermal energy. The questions I had were around, do we have a, or maybe it was presented and I missed it because they went so fast, some of the different categories, low density, residential, medium density, have a population or number of buildings for that, which might also help guide analysis. The low density residential, in some ways, the cost, I think, per was like $300,000. It seems at some point there's a, well, connecting houses that really far apart doesn't make sense, just up around right there. But that wasn't the exercise here. But I think that to really electrify the heating sector, it's going to be a mix of grids and individual buildings or small sets of buildings. I think the goal to connect all of them is theoretical and in some ways unnecessary. It's necessary when we have natural gas that comes up from New Jersey. It starts from New Jersey and then it kind of goes out to, you know, through Connecticut. But we don't need to have that as a constraint. I think the grid idea is terrific, but they don't all have to be connected. Many times, trying to get two connected to each other is going to be more expensive than it's worth. Plus, when we have any kind of system, and talk about pipeline, if you start from a source, a big pipe, and as you go out, sort of like your arteries, your capillaries. We don't need to have the constraint of starting from a single place. We can start a lot of different places. And we can also just start at a single building if we can balance the loads in that building. The last thing I just want to say is that on any time where we have too much heating capacity, so we're cooling more than we're heating, those are commonly balanced in the south. We have ground loops that cover the heating and then the rest of it. Now, a battery cooling tower is not so great these days, but maybe some combination of dry coolers and ground loops still get you to full electrification. But you don't need a separate air source system. It's all the same system that's inside the building. It just uses cooling towers.
Thank you, John, and thank you for driving from New York. So I think one of the things he just brought up is actually a really good way to end, which is we don't have to constrain ourselves to the limits we put on this study. We had to set limits somewhere and ask the question in some way to make their life bearable as they do the analysis. But there's really an enormous wealth of options in front of us, and I hope that you leave today really with the sense that there's one more option that we have in our arsenal to try to design the future. And so I hope the conversation continues, and I really, really ask if the one thing you do to help is stick that feedback card into the basket on the way out so that we get your feedback so we can